This is a video lecture covering the basic physics behind how the modern vacuum cleaner works. The science has been known for 250 years, yet no one on the internet has ever given it full and contextualized treatment before, to my knowledge. It's intended to be watched linearly, but does have chapters to help with referencing and subsequent rewatches. As a bonus at the end, common myths are addressed to improve understanding, to immunize against misinformation and marketing tricks, and to help you make informed buying decisions. When you turn on the vacuum cleaner, electrical power is used to activate the motor that turns an impeller to remove air from the machine, lowering the pressure inside. This creates a partial vacuum and gives the device its name. Air flows in from any openings to replenish the air removed and restore atmospheric pressure. Continuous inrush air can be used to drag in dirt from the floor in the process. To accelerate a dirt particle out of the carpet, the air moving into the cleaner head must exert a force on it. This is described by Isaac Newton's second law of motion. This force is a complicated, empirically determined fluid dynamical drag force that depends on the particle's shape, size, and the speed of the air flowing over it. The drag force the particle experiences scales with the square of the airspeed, but only linearly with all the other factors. This means the speed of the air flowing over the dirt particle dominates how effectively it's removed. Maximising the speed of air across a particle is thus critical to maximising the experienced drag force. Airspeed is increased by the cleaner head. When fully sealed to a carpet, the walls of a cleaner head act as a flow constrictor. There's a fluid dynamic effect that describes this, known as the Venturi effect, named after Giovanni Venturi, who discovered it, which itself is a special case of the Bernoulli effect, discovered by Daniel Bernoulli. The Venturi effect naturally follows from the need to conserve mass and ensure the amount of air coming into a bounded system is the same as the amount of air going out, and none is magically created or destroyed. The Venturi effect describes how the lower air pressure inside a sealed cleaner head causes an increase in the speed of a compressible fluid, such as air, as it enters through the narrow edge constrictions. This increasing airspeed increases the aerodynamic drag force, making dirt removal more effective. A cleaner head, acting as a bounded geometric enclosure that air flows through, is therefore a carefully engineered tool to make use of the Venturi effect to maximise the speed of air in the flow and impart a greater force on dirt particles to be removed as the head passes over. This is the Venturi equation that quantifies this phenomenon in fluid dynamics. It shows how the pressures inside and outside the head relates to the increase in airspeed as air enters the head. Rearranging the equation, you can see that the only factor affecting the speed of the air entering the head is the suction pressure. In other words, more suction gives higher airspeed. We know from earlier that this gives a greater drag force on the particles and thus better cleaning performance. Strong suction is thus extremely important for good cleaning results. All the equations can be combined and simplified to give an expression for the acceleration of a particle out of the carpet. This reveals that particle removal is not just determined by the cleaner's suction pressure, which is the only active aerodynamically relevant term, but also the properties of the dirt particle itself, such as its shape, size, and mass. So let's explore those other terms a bit more. The vacuum cleaner is designed to handle dirt in a large range of shapes, sizes, and masses. The influence of these factors is reflected in the particle-related terms of the acceleration equation. The drag coefficient, or how well a particle interacts with the air, depends on the dirt particle's shape and is lower for more spherical particles and higher for more complex shapes of the same size. The projected surface area, which depends on the orientation of the particle at a given moment relative to the flow, acts like a wind sail. Particles with more mass carry more inertia, making them harder to accelerate, like a small stone relative to polystyrene. These three factors are why heavy, spherical, or aerodynamically shaped particles, like sand, grit, and rice, can be more difficult to remove, whereas large, light particles, like fluff, dust, and hair, are easy to remove. Now that we know about the forces acting on particles to remove them, we can step back and look at the wider air circuit present in a vacuum cleaner. It's important to understand this circuit because it helps understand many different use cases later. It's well known in physics the analogy between electromagnetism and fluid dynamics, which applies to the vacuum cleaner. So, let's look at each core component of a vacuum cleaner and build up the corresponding equivalent electrical circuit. The main power source is the motor that supplies the energy to move air around. In electrical circuits, this is the battery or other power source which supplies the electromotive force. The motor itself also resists the air slightly due to Newton's third law. This creates what's called an internal resistance. Batteries in electrical circuits also have this. It takes energy to overcome this resistance, which will be important later, and is usually designed to be small to minimise losses. I'll come on to this more later. The motor moves air out of the machine, creating an air current, or airflow. The pressure inside the machine drops, and the weight of the atmosphere forces air into the cleaner head to replenish the partial vacuum created. But this is resisted by the presence of the flooring that the head is well sealed to, and is represented by a resistor. This resistor, i.e. carpet, is like a partially closed water tap which limits current or airflow. The circuit is completed since the air exhausted by the motor re-enters the atmosphere where it came from. Since the motor is forcing air out of the machine, there's a pressure difference between the inside and outside of the machine that drives airflow, much like water at different heights. This pressure difference is the suction, or voltage in electromagnetism, and you can measure that suction at the head, i.e. across the resistor. For completeness in the analogy, air is equivalent to charge, moving air is the equivalent to current, and suction is equivalent to voltage. Georg Ohm was the first to identify the relationship between voltage, current, and resistance. It's described by a simple equation which shows that suction is linearly proportional to airflow through a carpet pile with a given air resistance. In other words, more suction brings more air current through the pile. But as Newton and Venturi showed, only the suction affects cleaning performance, since that's what determines airspeed and particle acceleration, and the increase in airflow is incidental and not responsible for increases in cleaning performance. This debunks the widespread internet myth that greater total airflow gives better performance. Larger airflows are actually bad for cleaning performance, as I'll discuss shortly. First, we need to quickly discuss power. The power of the air expelled by the motor is measured in air watts, and is the product of the airflow and suction pressure. It's analogous to electrical power drained by the motor in operation, measured in watts, which is the product of voltage and current. The same air power can be achieved with low airflow and high suction, or vice versa, interchangeably. I'll discuss the advantages of having more air power shortly. Air power and electrical power aren't the same, and it's important you recognise the difference between the two in advertising. Often manufacturers of poorer products advertise the electrical power consumed by the motor in watts, since it's always a bigger number than the actual air power in air watts. Better manufacturers produce more efficient motors that can consume relatively less power and deliver more air watts than others. To understand why large airflows are bad, we first need to go back to the air circuit. The total resistance in the circuit isn't just the air resistance provided by the flooring, but also the internal resistance provided by the motor, discussed earlier. We can apply Ohm's law using the suction pressure provided by the motor and ensure both internal and external resistances are included in the total. This can be rearranged for airflow, which can then be plotted for a given suction level as before to show the relationship, choosing a small value for the internal resistance. You can then apply Ohm's law to the external resistance to find the corresponding suction at the cleaner head, and plot that as well for different air resistance values, i.e. flooring types. The benefit of these plots is that they show exactly why large airflows are bad. When air resistance drops on some floor types, such as loose shaggy rugs, then hugely greater airflows occur. As the airflow into the head increases, the suction correspondingly decreases, as the maths clearly shows. As we know from Venturi, this suction loss at the cleaner head reduces airspeed and impairs cleaning performance. Venturi showed that suction determines the speed of the airflow. Large leakage airflows enter the head more slowly and are less effective at cleaning. Plotting this also shows why the internal resistance of the motor needs to be accounted for in the air circuit. If it's set to 0, then you just have Ohm's law for the external resistance, and when you calculate suction at the cleaner head, it doesn't appear to change at lower air resistances where large airflows are present, which is physically inaccurate. The internal resistance of the motor can't be neglected. Combining these two plots, you can see that suction at the cleaner head is always lower than the ultimate vacuum strength of the motor, since greater energy is lost as the motor removes ever more air from the machine. Understanding this also helps appreciate why having more air power is beneficial, which is why we discussed that earlier. The suction pressure of the motor scales linearly with motor air power, and you can calculate from the earlier equations that the corresponding suction at the cleaner head in a given situation also scales linearly with the air power available. This means a greater air power allows the suction, and thus a higher airspeed, to be sustained in situations where high leakage air currents occur, such as on porous flooring or during above floor cleaning, both of which I'll discuss shortly. In other words, with more air power, you can draw in higher air currents before suction falls to a given level, helping maintain airspeed. Understanding why large airflows are bad also helps understand why it's important that the cleaner head has a good suction seal with the carpet. Examples of where this doesn't happen include the head not being sealed due to bad design, the head hanging off an edge during use, or other situations commonly seen where large holes and gaps are introduced. In the air circuit, the gap effectively offers a second, alternative path for airflow. Air current is split between travelling through the carpet pile and through the gap. The gap offers very little resistance compared to the carpet, so it's easier for air to flow that way, and so most of it does. You can calculate from circuit theory for parallel resistances that the net resistance of this situation is much lower, and so a much larger net air current flows. As we've seen, this then causes a voltage or cleaner head suction drop, and this reduces cleaning performance following the Venturi effect. For best dirt extraction, it's important to ensure that the cleaner head is fully sealed to the surface to ensure resistive load and avoid large leakage currents that reduce suction pressure and airspeed through the pile. The Venturi effect shows that high suction is important for getting good cleaning results. But if it's too high, then head clamping can occur. Following Newton's laws, when the pressure inside a floor-sealed cleaner head gets too low, then the weight of the atmosphere can apply a large resultant downward force on it, which can make it hard to push around. This clamping force also scales with the surface area of the cleaner head's opening, so bigger heads will clamp with lower suction. Any situation that increases suction pressure will make the head harder to push. This can be by vacuuming on flooring with higher air resistance, or by increasing air power. Demonstrating with air power is easily done by comparing power modes in some cleaners. The higher suction of boost mode makes the head clamp harder to the floor and tougher to move. Demonstrating with resistance is best done on smooth hard floors, where almost all the airflow can be cut off, reducing suction pressure to very low levels and hugely increasing head clamping force, causing the cleaner head to clamp like a limpet. If clamping becomes excessive because the head pressure is too low, the brush bar can strain as it's forced too hard onto the carpet and can draw the carpet into the cleaner head. This can cause the brush bar to slow down, and if resisted too much, can even stall. This is a built-in safety feature to protect fingers and carpets. While you could design a brush bar to brute force against this, it would risk carpet damage or personal injury. Well-designed brush bars with the correct level of stalling torque slow down on carpet when cleaner head pressure is too low, indicating bleed relief air is required on a given type of flooring, which is discussed next. Based on the background science discussed so far, cleaner head clamping is alleviated by restoring a reduced level of suction. When well sealed to the floor, this is achieved either by reducing the air power or introducing controlled bleed airflow. Good modern cleaners allow both of these with power modes and front gates. Front gates are favoured on hard flooring to allow large particles into the head and avoid snow ploughing. On carpets that cause clamping, it's commonly misunderstood that reducing motor power or opening gates to allow in bleed air reduces cleaning performance. It doesn't. As we learned earlier, Newton and Venturi showed that cleaning performance is driven by airspeed and that is controlled by suction pressure alone. On two different floor types that offer high or low air resistance, as long as the suction pressure in the head is the same, whether or not there's bleed airflow or using a lower power mode, the airflow will have the same speed and so be accelerating unimpeded particles just as effectively. Although different carpets may have other properties which net particles more effectively, making them harder to remove, and I'll discuss this more shortly. Above floor cleaning often involves an open tool, offering relatively lower air resistance that draws in larger air currents. As with a cleaner head, when the nozzle is bounded by a surface, airspeed increases following the Venturi effect. It also increases air resistance, reduces airflow, and increases suction pressure, which also increases airspeed. If there's a gap, like a deeper crevice, then there's less resistance and more leakage airflow relative to a flat surface, reducing suction and airspeed. As discussed earlier, higher air power is beneficial for above floor cleaning and allows for sustained suction and airspeed in the presence of these larger leakage currents, helping accelerate particles at greater distances, which cleans crevices better. Carpets can have porous or non-porous backing. Loose shaggy rugs tend to be porous, whereas good quality fitted carpets are more often non-porous and possibly with impermeable waterproof backing to avoid spills seeping into the underlay and causing rot. A carpet with porous backing or a loose shaggy rug offers considerably reduced air resistance, and so a larger current of air can flow into the clean head. This, as discussed earlier, reduces suction if there's insufficient air power to sustain it, and so reduces the airspeed and cleaning performance. This is why shaggy rugs can be slower to clean without sufficient air power. Suction at the cleaner head drops off and reduces entry airspeed despite the larger airflow. Motors offering sufficiently high air powers with enough air watts help sustain suction pressure and therefore airspeed in the presence of larger leakage airflows to achieve faster cleaning. This is why it can be helpful to use boost mode to clean heavily soiled rugs. The motion of air through porous and non-porous carpets is quite different. Let's consider non-porous flooring first. Airspeed within the carpet pile reduces with depth because the non-porous backing blocks air from underneath, and the carpet base is further away from the low pressure head where suction pressure is greater and airspeed will be higher. To illustrate this, an example trend can be plotted with the mathematical relationship shown, whose derivation goes beyond the scope of this lecture. The exact profile will depend on the nature of the carpet. The purpose of this, though, is to better illustrate that there will be a depth for a given carpet type where the airspeed is too low to impart enough force on dirt particles down there, so they won't get removed. This is easily demonstrated by artificially injecting dust at the very bottom of a non-porous fitted carpet and noting it can't be vacuumed away. However, it's difficult for dirt to ever naturally reach a depth where it can't be removed because the fibres act just like a physical filter and block particles from getting there in the first place. Almost all dirt remains in the upper regions of such dense carpet piles with regular cleaning. Flooring with a porous backing, such as a loose rug, is much simpler. Since air can flow from underneath, the airspeed near the backing can remain relatively high. However, the airspeed in the upper regions may be relatively lower if the high air currents reduce suction sufficiently and there's insufficient air power to sustain it, as discussed earlier. For both flooring types, dirt on the surface of the carpet is more easily removed, since particles can get netted and trapped by the fibres on the way out from deeper down, preventing even higher air speeds from being effective. This is one of the reasons why carpet agitation is beneficial. Agitation is the process of jostling the fibres of the carpet and provides three key advantages. Firstly, moving the head over the carpet can directly grab loose material, like hair, on the surface. This is helped by bristles on a rotating brush bar that grab and sweep the particles into the airflow, where the aerodynamic forces can accelerate them away. Secondly, a head moving over a carpet can broadly bend and flex the fibres in the direction it's moved to open gaps in the pile. The combing action of the brush bar itself can also separate pile to open gaps. An open gap has locally reduced air resistance since there are fewer fibres in the way, allowing a higher airspeed in the flow, applying a greater force on the dirt particles and removing them faster. Thirdly, moving the fibres shakes free any trapped particles that might get netted as they move out in the airflow. The cleaner head simply rubbing over the surface achieves this, but the effect can be multiplied by a rapidly rotating brush bar, whose bristles jostle the pile fibres many more times per pass. Directly surface sweeping, opening pile, and jostling fibres all ensure the maximum aerodynamic drag force is applied to particles and minimise any re-netting as particles leave to increase the likelihood of their removal. This is why heads with rotating brush bars typically achieve better cleaning results than simple suction heads alone. It's important to note that agitation has minimal value if the particles experience low airspeed from reduced suction pressure. If the particles are not effectively aerodynamically accelerated away, it doesn't matter if they've been dislodged by agitation. This is apparent when a machine loses suction because it's blocked and the particles remain, even though the agitation action is operating correctly. Since carpet acts like a blocking filter for dirt, some will always get netted on the way out. Repeated passes gradually remove additional remaining dirt. The more dirt that's in a carpet on a given pass, the more that will be removed during that pass, with diminishing amounts removed each subsequent time when there's less left there to be removed. This can easily be measured and plotted as shown here. Removal of dirt particles is therefore a stochastic, statistical process with dirt concentrations reducing with each pass with a geometric relationship that will depend on all the factors discussed so far. This includes the machine properties that affect suction and airspeed, the particle properties that affect the response to airflow, and the properties of the carpet they're trapped in. Vacuum cleaning is therefore never about removing all the dirt, but about managing dirt buildup and reducing concentrations to an acceptable lower level. The universally accepted golden standard method to quantify the relative cleaning performance between products across all floor types is independent comparative industry standard testing. This is expensive and time-consuming, needs to be conducted by trained professionals in a laboratory using specialised equipment, and requires a lot of statistical analyses. Only the manufacturers can afford to commission this, but it's rigorous, statistically significant, and independently verifiable. Performing comparative testing at an amateur level is doable, but can never be as rigorous. Any test methodology used needs to be representative, reproducible, and capable of capturing the statistical nature of dirt extraction from carpets discussed earlier. I'm aware of no amateur testing on YouTube or behind profiteering consumer magazine paywalls that accurately meets these requirements. The stochastic removal of dirt needs to be measured in a controlled and representative way. This includes things like the type of flooring, how it's prepared and checked, the type of dust used, which should be representative of fine household dust, not piles of sand. It also includes the amount and distribution of the dust loading in the pile, the speed of the cleaner head over the carpet to ensure the aerodynamic force is applied for the same time, representative overlapping, and so on. These important and representative controls are lost in all non-industry standard testing I've observed on the internet, and so cannot be taken seriously. It's important not to be misled by the cowboy testing out there. I've gone to great lengths to achieve this level of control in testing conducted on this channel. Results are best shown by plotting cumulative dust extracted as a function of the number of passes from the same initial conditions. This allows the relative cleaning performance between different machines to be directly compared for real-world representative conditions, apples to apples. There are lots of different carpet types with varying pile lengths and densities. Deeper pile carpets tend to be more difficult to clean, since dirt at depth experiences lower airspeed and has more opportunity to be netted, so it takes longer to reduce dirt concentrations. However, very short pile carpets, like those typically found in offices, can offer high resistance to airflow, and even moderate air powers can produce large suction pressures and cause head clamping. Loose rugs with low air resistance can allow a lot of bleed airflow that reduces suction pressure and airspeed, making it harder to clean, as discussed earlier. Every carpet is different, and cleaning performance on one carpet type won't be the same on another. Each machine being compared needs to be tested on the same carpet. Industry standards test on many different carpet types to produce a geometric mean of performance across all common floor types, and this is another reason why they're considered the golden standard. It's easy to brute force performance by using an overly powerful motor, but that often means it'll be heavier and deplete batteries faster on the better stick-vac form factor, and consume more environmental resources. The art of cleaner head design is to maximise high airspeed throughout the pile using the minimum energy possible, and research continues to find new ways to achieve this. This is why measurements of motor properties alone are not good indicators of performance, since good design can allow more with less, and simply assuming more power is better between different products is misleading. Cleaning performance needs to be directly measured, along with the power consumed to achieve it, to identify better technology. As discussed earlier, the three key considerations to understand how to achieve the best cleaning performance are the motor and cleaner head properties that affect suction and airspeed, the particle properties that affect the response and the airflow, and the properties of the carpet they're trapped in. Understanding this physics shows best cleaning results are achieved by maximising the time that high airspeed is travelling through the pile by having high suction, whilst it's being flexed repeatedly by a brush bar to release netted dirt between the fibres. It's good to move the head reasonably slowly on both forward and backward strokes, and let the cleaner head simply groom the carpet for you, which is also less tiring with higher suction levels. The slower movement increases the time aerodynamic forces are applied to particles, and more will be picked up in the pass. Passing over the carpet with a 50% path overlap will double the active particle removal time. Greater overlaps will ensure any one area gets even more passes and will get better cleaning results. This just needs to be balanced against the time you want to spend cleaning, and is why on-demand, bite-sized cleaning, rather than regimental whole-house mega-cleans in one go, are better suited for many. On hard floors, overlapping strokes is less necessary since they're mostly surface swept by good cleaners. I'm aware of no convincing evidence to suggest that the direction of vacuuming is important if the above steps are followed. Very heavy spot messes that are visible can additionally benefit from more air power from boost modes to reduce the very high initial concentration and bring it more in line with the concentration found in typical initial mess levels. Better cleaners will reach a pickup plateau level relatively more quickly, and reach a relatively greater overall cleaning level. Once dirt has been collected by the cleaner head and makes its way into the machine, it needs to be separated from the air. This is usually done in stages, discussed next, gradually reducing the size of the particles removed and leaving air expelled by the machine with a very high purity. Early separator technology fed the dirt-laden air through a porous bag, which mechanically netted the dirt. As dust loading increases, the number of free paths for air gradually reduces, increasing air resistance. You can see from the circuit diagram and equations that as the bag's air resistance increases with dust loading, the airflow drops, which in turn reduces the suction pressure under the sealed cleaner head. You can plot how cleaner head suction drops as a function of bag dust loading. To compensate for this loss of suction, the machine would need to supply a greater motor air power and increase power consumption. Otherwise, airspeed through the pile would reduce substantially following the Venturi effect, impairing cleaning performance. This was the major weakness of this technology. It also suffers from ongoing running costs to replace bags to reset the bag's air resistance to a low value, has a higher environmental impact as bags are added to landfill rather than just the dust, an inability to see when it's full, and festering of foul odours. Successor technology utilised inertial separation methods. The Venturi effect was employed within the primary dirt separator by constricting flow to dramatically increase airspeed and create a jet. Feeding this jet into a cone meant the dirt always changes direction and is therefore subjected to a centrifugal force following Newton's first law, gradually spinning towards and then out of the bottom opening. This allowed the dirt to be inertially separated from the air by virtue of its higher mass, whilst the cleaner air then escapes from the top of the cone. This cyclonic technology ensured air resistance was independent of dust loading, ensuring no gradual suction loss, maintaining high airspeeds and dirt pickup performance during operation. In the equations, the cyclonic resistance is constant, as is the corresponding airflow, and thus suction through the carpet at the cleaner head. Plotting suction for both technologies shows why cyclonic technology does lose suction with dust loading, and why it was an important improvement over bags. The disadvantages of the technology are that the flow constrictions needed to create high-speed jets, necessary to generate the large centrifugal forces, cause a loss of differential pressure, which needs compensating for from the outset by a higher pressure motor capable of generating sufficient motor air watts. In other words, it can be relatively more energetically expensive to operate than simple mechanical separation processes, although highly optimized and efficient cyclonic design over the years has optimized this to be better than systems using dust-loaded bags. Cyclone packs are also quite bulky and take up space. Cyclonic dirt separation systems typically employ a pre-cyclonic filtration process in the bin. Dirt-laden air entering the bin is jetted utilising the Venturi effect, with the narrowing of the passage to increase speed and cyclonically spin inside the bin. This is a large initial cyclone, causing dirt to be centrifuged and dropped to the bottom. This filters the largest of dirt particles. This can be semi-separated with a flexible rubber skirt to help retain the dirt at the bottom, particularly when tipped upside down. Smaller particles can escape this relatively weak cyclone and move towards the shroud that is a mesh of very small holes a fraction of a millimetre in size. The smallest particles pass through and are handled by the smaller cyclones discussed earlier, but larger particles can aggregate on the edges of the holes. This metal shroud therefore acts as an embedded mechanical filter, similar to the old bag technology, and is its greatest weakness. It gradually clogs and requires manually scraping to avoid a reduction in suction pressure, which on some better machines is done automatically on emptying. After expulsion from good cyclonic filtration systems, air tends to contain very few particles larger than a few micrometers in the best designs. Downstream, mechanical separation is sometimes relied on again in the form of a premotor filter. Much like in the old bag technology, the fibres and gaps between them are smaller than the particles they capture, and so net straggling particles large enough prior to the air entering the motor. While these filters are equivalent to fibre bags, they're now the last line of defence rather than a first, and so see very little dirt, preventing them from clogging for a very long time. They can therefore be smaller and only need rinsing occasionally. Air exiting the motor is often fed through a final HEPA filter. These filters don't operate on the same principles as other filters and rely on physical processes described by classical colloid filtration theory to separate very small submicrometer dirt. On these scales, fluids, like air, containing very small particles, down to 100 nanometers, behave like a colloid suspension, in other words, like raisins in jelly. Particles don't gravitationally sediment and instead remain suspended. These particles can be made to aggregate through orthokinetic means by the flow of air, or perikinetic Brownian diffusion-based processes, i.e. random bombardment by air molecules. The presence of the HEPA fibres also helps with this flocculation process to accrete these small suspended dirt particles. The larger of these tiny particles, with sufficient inertia, can impact and sediment. Smaller particles with less inertia to impact can graze the surface of a fibre and be captured, which is called interception. And the smallest particles with insufficient inertia that are affected by the air molecule bombardment process of Brownian motion, as advanced by Albert Einstein in his famous scientific paper, can randomly walk and contact the HEPA fibres to be captured in the process of diffusion. The particles that contact a HEPA fibre's interface and flocculate do so because it's electrochemically energetically more favourable. Not all particles remain flocculated, and not all even contact a HEPA fibre, so filtration is never 100% effective. In other words, as with dust removal, it's stochastic, and HEPA filters reduce dirt concentrations rather than fully eliminate. The effectiveness of HEPA filtration is very precisely defined in industry standards, and the minimum H13 grade of a HEPA filter must remove 99.95% of all particles larger than 300 nanometers. Since the creation of jets by constricting flow to increase speed following the Venturi effect causes differential pressure losses and is energetically expensive, research has found other more efficient methods of dirt separation that are non-cyclonic. In the short term, the first stage cyclone is likely to be substituted by a non-cyclonic inertial dirt separation system that achieves even better filtration results than using a bin cyclone and mesh, and using less energy. With this design, air enters the bin along the outside of a central column with a U-shaped profile on its concave side. About 80% of the air goes through an ultrafine mesh into the central column. About 20% is curved out because of the U-shape and into the main bin, which then passes through another mesh on the convex side of the U-shaped centre column to join the 80% that went through the first mesh. Large particles can't get through the mesh and have too much inertia to get stuck on it, and the inrush air continuously aerodynamically washes it. Instead, it gets flung out into the bin by the U-shape. This mesh therefore doesn't clog as easily, even upside down, and the pores can be reduced to as small as 100 micrometers, making it separate dirt even more effectively. A separator of this design has several advantages. It doesn't require enhancing the airspeed in the form of jets to create high centrifugal forces, avoiding cyclonic pressure losses and therefore consuming less energy, which helps with battery life. The air flows in a straight line across the bin with little turning, which also helps reduce energy losses, following Newton's laws. Not needing to create an initial jet to spin around the bin allows for wider diameter tubes that help prevent blockages where larger particles are collected. There's no recirculating of airflow like with the current cyclonic and bin shroud design, which means long hair doesn't wrap around the centerpiece. This should also help avoid bin clouding caused by particles creating tiny scratches in the bin surface that scatters light. The shroud shouldn't now block up before the bin is full, even when upside down, because the main flow into the machine and through the primary mesh is isolated from the accumulated dust in the main bin. It also gives more bin space to hold more dirt. The air from this system then heads on to a traditional cyclone pack for removal of much finer dirt before heading to the filters. Longer term, all cyclones may be eliminated, resulting in substantial energy savings whilst keeping separation efficiency independent of dust loading and the other advantages of a mechanical separation. This may be achieved by using a rapidly rotating disc with a porous mesh. Dirt-laden air entering the bin strikes the rotating disc, is given angular momentum by its rotation, and dirt is centrifugally flung out into the bin. The air path is linear through the machine, and most dirt contains too much inertia to pass through the mesh. The rapid rotation flings off any aggregated dirt, keeping it clean. Research has shown that it can achieve cyclonic levels of filtration. The major additional advantages of this design are: the air path is linear through the machine, minimising energy losses. The dirt separation efficiency remains at maximum, independently of the airspeed, unlike cyclones, which filter better with higher airspeed. Bleed valves to avoid head clamping can then be replaced with pressure sensors and variable motor control for more efficient energy consumption. The need for shroud scraping is eliminated. There are space and weight gains from the loss of the bulky cyclone pack, and there'll likely be fewer issues from trapped material along the air path causing odours. The air exiting the rotating disc separator then heads off to the filters. It's quite possible that both the first stage non-cyclonic inertial separator and the rotating disc separator can be combined in the same design. Most of the dirt is removed initially at the first stage in the bin, and the work of removing the fine dust that would require cyclones can be replaced with a rotating disc. The ultrafine discharge from the disc can be routed just as the cyclonic discharge is currently. Thank you for watching this lecture, and special thanks to all the brilliant scientists who devoted their lives to understanding the very difficult physical principles that engineers could later use to develop technology that facilitates the chore of cleaning. To finish off, I'll talk through some of the most common myths. At this stage, enough science has been discussed to now be able to debunk many of the common myths and deceptions out there, to help protect from being misled and deceived. Possibly the most common myth is that more airflow means better cleaning. We've known for the last 250 years, from the work of Newton, Venturi and others, that aerodynamically, suction alone affects particle acceleration in a flow. As long as there's meaningfully significant airflow, its total magnitude flowing into the head has no direct bearing on particle acceleration and only varies incidentally. We've also learned that, in fact, an increased total air current contributed from bleed sources reduces suction, and therefore the airspeed and cleaning performance. Venturi showed that suction determines the speed of the airflow. Large leakage airflows enter the head more slowly and are less effective at cleaning. The opposite to the myth is actually true. It's important to identify sources that refer to needing more airflow in the context of cleaning performance, since this demonstrates a lack of understanding of well-established and old science and indicates an unreliable source of information. A suction meter on the hose measures the suction pressure at near infinite air resistance. This is only ever achieved at the cleaner head when it's clamped immovably to a hard floor. The cleaner head suction varies in use depending on the net air resistance on different types of flooring, whether bleed valves are open, and the magnitude of motor air power. Only resultant suction pressure at the cleaner head is relevant, since that determines airspeed through the pile and thus the cleaning performance. Furthermore, technological advances that can better utilise resources may allow better cleaning performance using less energy, which also isn't captured by measuring suction alone. Measuring suction at the hose is completely irrelevant. The dirt removal trends under carefully controlled conditions should be measured instead. Look out for all sources that perform pointless hose suction measurements, as it's a hallmark of misunderstanding and their output should be completely disregarded. Similarly, measuring airflow at the open hose or by attaching a cleaner head to a box with a large hole in it, is completely irrelevant. By measuring at the open hose, or putting a large hole in a box, large bleed airflows occur. This wouldn't happen when the cleaner head is sealed to a floor and under resistive load. The two situations are very different, as shown earlier with their corresponding air circuits. The measurement case introduces a small parallel air resistance, dramatically increasing net air current. As is known from textbook science, the total magnitude of airflow is not relevant to particle acceleration at the cleaner head. Ironically, large bleed airflows introduced in such measurements would actually reduce suction at the head, and thus airspeed and cleaning performance. Again, the dirt removal trends under carefully controlled conditions should be being measured instead. It's important to identify and disregard any sources which measure airflow and conclude the cleaning capability of a machine, as they simply don't understand the relevant science. Look out for old-fashioned low-suction machines being tested on low air resistance porous flooring, like rugs. This is done deliberately to bypass the suction limitations of the machine and exaggerate its apparent performance. The machines typically have sufficient air power to sustain reasonable airspeed when large inflow currents are present on porous flooring and achieve acceptable cleaning performance. On non-porous, more air-resistant flooring, the lack of high suction motors prevents high airspeeds. As a result, their cleaning performance drops, but this is never shown. This can be demonstrated by measuring relative cleaning performance using carpet with low and high air resistance, using machines with low or high suction motors that can both deliver high motor power and air watts. Performance of both machines is comparable in situations where high suction isn't required, since both provide sufficient air watts to sustain suction pressure and high airspeed. On high air resistance flooring, where high suction is required, the machine without a high pressure motor performed considerably worse. You can also see how increasing the suction pressure in higher power modes on high resistance flooring improves performance, as expected from the Venturi effect. Good modern machines offer both high suction and high air power to achieve high air speeds in all situations on all flooring with varying resistance levels. Look out for sources of online misinformation that only ever test these low suction machines on porous flooring with low air resistance. It's misleading, and now you know why. Most dirt by particle number in carpets is microscopic dust that's more likely harmful to health. Industry test standards, in fact, use replica test dust with a size distribution that reflects this real-world condition. Poorer sources of amateur testing online use sand alone and often artificially inject deep into carpet, bypassing the natural filter-like properties of the pile, making things unrepresentative from the outset. If only sand is used in testing instead of fine dust, it's important to disregard any conclusions, since they're not representative of real-world conditions, which recognises particles far smaller and more difficult to remove from the pile. A common myth is that violent, very noisy vibration is beneficial to cleaning performance. Visually impressive particle bouncing outside the cleaner head is used to imply that cleaning performance under the head is improved. As discussed earlier in the agitation section, this is false. High suction and pile separation of fibre jostling result in the maximum airspeed used to accelerate particles. Extreme vibration is usually a result of poor design, where the bristles on brush bars protrude too much and physically impact the carpet too strongly without contributing further to pile separation. This at best causes a lot of noise, and at worst can wear carpet more. Seeing particles bouncing outside the cleaner head is irrelevant, since dirt is only removed under the head. This bouncing effect also doesn't occur directly under the cleaner head, because the weight of the head, combined with its suction, presses down on the carpet and prevents the free oscillation. The high amplitude oscillations only occur outside the head, where the often loose rug is freer to vibrate. Furthermore, only the large, visible, denser particles bounce, and the more harmful microscopic dust doesn't respond to impact vibration. If suction is lost, but the violent noisy vibrations continue, the particles under the head won't be removed. Evidence of all this is clearly seen along belt strips, where a line of dirt is left behind despite heavy vibrations occurring outside the head beforehand. Don't be fooled by visual particle bouncing, and look out for those that are. Only measured particle removal curves matter, and those that embellish vibration never show any. Examples of agitation myths can be seen in misleading demonstrations that show coloured sand bouncing up from a rug and imply their machine causing that is automatically better relative to the machine that doesn't. This deception uses several forms of misdirection to try and fool you, and this is how. The setup is always a loose, non-porous rubber-backed mat rather than fitted carpet with a large quantity of artificially injected coloured sand. The reason for using a loose rubber mat is because it's bouncy. The overly aggressive brush bars that cause damage to pile over time cause the mat to violently flap up and down in a way that wouldn't normally happen with a fitted carpet. It's the loose, bouncy rug rather than the brush bar that flings the sand upwards in a visually impressive way. Sand is used specifically rather than representative test dust because sand can be launched by the rug whereas dust can't. It's implied that if the sand bounces, then it's automatically been removed. As we know from agitation myths, this is false, and only particles under the head that are aerodynamically accelerated out are removed. If there's poor suction, then they'll remain there even if they're bouncing. They know this, and it's why they never show a second pass after the first, to hide that sand would still be bouncing and that the cleaner failed to collect most of it the first time. On rare occasions, they slip up and make a second pass, showing exactly this. Real comparative test data showing removal trends on fitted carpets is never shown, especially with representative test dust that doesn't respond to extreme vibration. I've linked an example to this trick in the video description so you can learn to spot this practice and not be deceived. The manufacturers of some cleaners without extreme vibrations, yet which agitate pile optimally, do present conclusions from industry standard testing, showing they outclean other machines, and confirming that heavy vibrations are not necessary. In common tests to attempt to tribally champion one brand of product over another, it's sometimes suggested that sand left at the base of a carpet causes damage and wear. This is often paired with misleading tests where sand is artificially injected to the base where it would never normally be, bypassing the filter-like properties of a carpet. There are also all the usual tricks, including using a loose porous mat to eliminate the reduction in airspeed near the base. No evidence is ever provided of claimed carpet damage from grit. Simple observations of very old commercial entrance doormats, aggressively wiped on by hundreds of people that had sand and grit in its base for years, showed no evidence of claimed damage. Some salespeople attempt to suggest that a cleaner that can suck a lightweight tube to the cleaner head is therefore better by implying stronger suction. The irony is that to impart forces onto tubes outside the cleaner head means there must be fast-moving air outside the cleaner head, caused by substantial leakage currents into the cleaner head. As we've seen, this reduces suction pressure under the cleaner head, reduces airspeed, and impairs cleaning performance. Any machine that can grip a tube almost certainly has a leaky, inefficient, and poorly designed cleaner head, unless suction relief gates are deliberately open. An example of this deception is provided in the description. So-called big mess tests often rely on absurdly exaggerated initial mess levels. The implication is that any cleaner that can cope with such a big mess must automatically be capable of getting good cleaning results. It seems so sensible at first thought, but it's a deception. It's easy to remove dirt when there's lots to be removed, and the dirt removal curves clearly show this. Absurdly high, exaggerated initial concentrations are totally unrepresentative of real-world conditions. A machine that can handle an absurd amount of dirt in one go might not be good at cleaning well when dirt concentrations are lower and more representative. This is because it's more difficult to remove real-world levels of dirt, which require high suction and good design to make best use of available resources. Likewise, in the reverse situation, even if a machine isn't good at removing absurd, exaggerated amounts of dirt, doesn't mean it isn't better for real-world conditions. It's important not to conclude the effectiveness of any machine from usage in these absurdly exaggerated situations. Poorer sources never make it extremely clear that such behaviour has no meaningful merit beyond cosmetic entertainment, so it's important to identify any sources of such testing and disregard.